The first talk is on software testing, and as before, we are not going to tell you all the details about what testing is, the definitions, etc., etc. All of that you can find on the web easily, because our focus here is on telling you about things, telling you about practices, how to build tests, etc., that is not so easy to find elsewhere. So that's where our focus of the testing module is. However, you still have to think about testing practices, because more often in the scientific community than anywhere else, people will sometimes tell me that testing is too much of a tax on their time, that they don't have time to do testing. And that leaves me scratching my head, because if you're not doing testing, how do you even know that the results you're getting are correct, right? So as you're developing the code, something you must be doing to convince yourself that the code is doing what it is supposed to do. And so you're effectively testing. It is just a matter of converting that into something that you do on a regular basis is all you really need to do in order to adopt practicing. But testing practices, you want to not just make sure that your code is running correctly, but that when you're using it to do science, you want to capture other information about it that assures you about the quality of the results that you're generating, because there are all these stakeholders that need to have confidence in your results. First of all, you yourself, because you're writing a paper. Imagine how embarrassing it would be if you wrote a paper and then it turned out that your code didn't work right and that you have error in your data. And similarly, others like your project lead, boss, your reviews, referees, your readers, they all need to have confidence in your data that you've actually done the science that you claim you're doing. And so testing helps build that kind of credibility in your science. So we are not delving deeply into the issues of verification and validation, and here it is worthwhile pointing out that the scientific community views verification and validation somewhat differently from the software engineering community, and it is good to be aware of both. In both cases though, verification talks about having the right implementation, and validation is more about whether your design addressed the outcome you wanted it to have. So in scientific computing, verification is convincing yourself that the method that you have written is doing what you wanted it to do, which means that the method is implemented correctly. In software engineering, what that does is it makes, to a software engineer, what that means is that the software conforms to the specifications. Again, validation for the software engineering community means that the software is doing what the customer or the client wanted it to do. In scientific computing, validation typically means that your science, the method that you have written, is actually reflecting the reality that you want to capture. The model that you have built is that it is conforming to that it is the correct model, and therefore typically a scientific validation runs against some form of observation. That observation may be a straight up observations like in cosmology and astrophysics, or it could be an experiment that you're running and you're using that to validate. Question arises, when should tests be provided? When should you build tests? And the ideal answer is that tests should be going hand in hand with your development. Better still, the strong advocates for test driven development will tell you that you should write your test before you've written your first line of code. And there is a good reason for doing that. It is because if you start to write the test before you've written any code, what you have to do is you have to think through what is it that you want that particular code to do. and what does it mean for that code to be right or wrong. So, in that sense, that effectively becomes the specification for the software that you are trying to write. What this also means is that if you are writing your tests as you are developing the code, that your code is tested more often because you will have automated that, etc., etc. Now, I am not aligned with the very hardcore rule of test driven development, and this is because many a time when you are writing a piece of scientific software, you do not yet have clarity in your own head about what is it that you are trying to write. In many cases, you are designing as you are writing your software. So, I would say that in my mind, test driven development that is adequate for scientific computing is you have this cycle of writing code writing, testing, etc., etc. In that loop, somewhere there should be a test written and hardened and continue to harden as you go along in the process. So, this is the loop for writing for test driven development, is that you write one test that describes one aspect of your program, and then you of course, the first time you run the test it is going to fail because there is nothing that has been implemented, there is no feature yet at all. Then you write just enough code to make that test pass, then you refactor the code and then you repeat creating new tests as you add new functionality. In some sense, even what I was talking about in terms of design, you could do this if you strictly followed this, but this is the general principle, is that any aspect of your program that needs to be, that you want to verify for correctness, you should just be writing a test for it. So, within the software development cycle, you may need to do different types of testing. This is a general model of what software development life cycle will look like in scientific computing, where your typical situation is that there is the physical world around you and you got interested in some phenomena within that physical world that you want to model and understand better. What you do is you create a model for that phenomena that is in some sense a set of equations that capture its behavior. Once you have those set of equations, then you will figure out a way of discretizing them, because that is what you need to do in order to write code for it. And then you will find numerical solvers that apply to those discretizations. You will do the implementation of those numerical solvers, and then what this loop is doing here is the validation, where you are confronting it with observations of some kind. And also, if you are running it on HPC platforms, you will want to worry about performance because you want to use the platform well. There are these feedback loops, because this is not a single step sequential operation that can go on, because you write your numerical solvers and so one of the tests that you have to do for when you are writing numerical solvers is for stability and accuracy, order of convergence, etc., of your numerical method. That is as much a part of testing as correctness itself is. But then also what can happen is you look at the numerical solvers and you find that it is not meeting the model fidelity requirements that you have. So, you may need to go back and you may need to reformulate equations. Similarly, when you confront your results against the physical phenomena for validation, you find that it is not capturing the model as you should. So, you go back to drawing board and you rewrite the equations. In addition to that, within numerical solvers, you may have a feedback loop for equations implementation, etc., etc. So, this is the very complex world of scientific software development cycle, in which you need to be doing various tests of different types at various stages, and some of these verification or somewhere in there are diagnostics as well. For example, for verifying the accuracy and stability, you will develop some kind of diagnostics. You will want to see if you are writing a second order method, that it is actually a second order method. Similarly, you will want to check for whether the results stay stable, what kind of regime do the results stay stable. And then when you are writing a numerical method, you will have to, and it's trying to capture a phenomena, you will probably try to think of some ways in which you can tell if that phenomena is captured even if you do not have direct observational data. For example, you may want to do some kind of a statistical analysis, you may want to do some sort of an indirect analysis, many things that whatever you do in order to convince yourself that your implementation is correct becomes part and parcel of testing. So, that brings us to the question about how do you develop tests. We want to verify correct behavior, but how do you go about doing that? So, even as you start to write a code, you start to think about ways in which you are going to be able to tell if the code is running correctly. And if you have had any experience writing non-trivial code, you will have realized that you need to do this in small chunks. That you write a small chunk, you convince yourself that that small chunk is correct, then you go on to add more, and you continue to convince yourself that whatever you are adding is not breaking the code from before, etc., etc. So, you are, whether you want to or not, whether you admit it or not, whether you realize it or not, as you are writing the code, you are thinking about ways in which the code is doing what it is supposed to do. Many a times you may be doing it again by confronting the code against a known analytical solution. So, for example, you may have written a method for which can be applied in a situation where there is a known analytical solution, and so therefore, you can confront the obtained results against a known analytical solution. A simplest example of that is when we do, if say you were writing a code for calculating the Fourier transforms. We all know that in a single sine wave returns a sine wave is a single point in the transform domain, and vice versa. So, that becomes a symbol, and that is too simplistic, but that becomes a way of making sure of verifying that your Fourier transform code is correct. Then there is a comparison against manufactured solution. The manufactured solution can happen in many ways. You can write something manually, do something manually and provide answers to yourself, and then you may make your code do it, and then you compare against the obtained solution, and that is what we refer to as a manufactured solution. So, right there you have all the ingredients you need for building tests, because all that you need to do is whatever you are doing manually for these steps, comparing against analytical solution, comparing against manufactured solution, if you just wrote a driver that would do both aspects, in the sense that do this part as well as run the same input through your written code, you already have a test, right. At other times, you may not be able to do things like either of those things, and sometimes you may want to have visualize and inspect the output. You so visualize the output and then you inspect the output. Now, what do you do if you want to turn it into a test? If you were to create a comparison utility, then you can turn your output into a baseline and you can do a comparison. Next time when you run the code, you can do a comparison against this visually inspected blessed baseline, and then you can work with that, and that becomes your test. And then, as I mentioned, there are ways of developing diagnostics, such as indirect ways of verification. In our world, for example, in FlashX, we are working with finite volume codes, and so therefore, one important thing is that all the physical quantities need to remain conserved, which means that this is all we need to do. That is the first, your canary in the coal mine, in that if any of the quantities does not remain conserved during the computation, then you know that your calculation is going wrong even without inspecting the outcome and so on. And so, most of the physical, you can rely upon the knowledge of the domain that you have in which you are trying to operate to think about diagnostics, which will indirectly tell you if your code is going in the wrong direction. Including these kinds of tests in your automated testing is important, and other things that you can do for this is, for example, have no error bars, because at times you may want to think about a situation where there is a slight change in your answer. Now, you do not know whether that say you moved to a new platform and your results are not identical to what they were on a previous platform. Now, you want to be able to differentiate between that difference in results which is happening because of machine precision, because there is a quantization error coming in, because the machines are operating in slightly different, so the floating point truncation error, or that this is really truly a perturbation in the solution that is causing these differences to occur. So, you want to have ways where you can tell that, where you can say what is the cause for these differences, and including those in tests is important. For a new code, if you are trying to develop the approaches that you take for developing code for testing for new code is different from what you might need to do for a legacy code. I recently learned the terminology, so I will share it with you, is that when you are developing a new code, what you are doing is white box testing, and when you are working with a legacy code, what you are doing is typically black box testing. White box testing is when you can modify the code as you are testing it, and black box testing is when you cannot modify the code at all when you are trying to test it. Okay. So, as you start to build your code and you start thinking about tests, the first line of defense is unit test, which means that for whatever code you are trying to write, think about, is there a simple relationship between input and output for that particular code? If there is, you should definitely exploit that, and that will give you a simple unit test. So, sometimes sometimes even if there is not a simple dependency like this, if you have simple dependencies that can be manufactured, then also you can build a unit test. There are other functions where you do not have such simple relationships, or that they have dependencies of the kind where building a mocked up input is so complex that it is almost not worthwhile. So, here what you do is you start to apply scaffolding, and the idea of scaffolding is that you start to build tests. So, you build say 2 tests, these are 2 unit tests. Now, there is a third test, which if you have the first and the second tests passing and the third test failing, that pinpoints another code component that might be the cause of that error. And similarly, you just keep on building in such a way that the failure pattern helps you pinpoint where your error might be occurring. And I want to explain that it is the easiest explained with a specific example. So, the example is that we have a problem, this one also comes from Flash X, is that we want to run shock hydrodynamics with adaptive mesh refinement. How many of you are familiar with adaptive mesh refinement? You have all heard about adaptive mesh refinement this week. So, that is a stupid question. You all know adaptive mesh refinement. Okay. So, now, you also know that in adaptive mesh refinement there is much more bookkeeping that goes on than just uniform grade, in the sense that even if you are running stencil code in adaptive mesh refinement, you need to have reconciliation of quantities at fine coarse boundaries, you do regridding, etc., 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 right. So, to get back to our example, the components that we need for running a shock hydrodynamics with adaptive mesh refinement is, you have to have a mesh, of course, because that is your domain. You need to have a hydrodynamic solver, you need to have some equation of state, and you want to parallelize it. So, first thing you do is you think about a situation where there is a problem that you can code where there is an analytical solution for a shock hydrodynamics problem, and it so happens that there is. This is the Sadov blast problem. This problem is that if in a domain, if you place a pressure spike at the center anywhere in the domain, a shock wave goes out radially in all directions equally. and the distance that the shock wave has traveled can be computed analytically. So, this is the basis on which we are going to build our testing scaffolding, right. So, the first step is we want the easiest thing for which you can build a unit test, a test where there is no external dependency, is the equation of state. An equation of state is what you need to reconcile the thermodynamic quantities and close the loop of the equation. So, these are solvers for Eulerian equations, and you need equation of state to close the loop. So, equation of state, you can, if you provide internal energy and density, it returns pressure and temperature. If you provide density and pressure, it returns internal energy and temperature, and if you provide density and temperature, it returns internal energy and pressure. So, what the simplest so the simplest way to develop a test, and this can be done on a pointwise basis, which means that you do not even need a mesh in order to run this test, in order to have this unit test. So, what you do is you initialize the code with some known value of internal energy and density, say, and generate your pressure and temperature. Next, you call the equation of state again with the newly generated pressure and density and generate internal energy. And if you want to be even more cautious, you can call the same equation of state, this time with density and temperature, and generate internal energy and pressure. At the end of it all these quantities should be identical to whatever you started with, and that is your equation of state unit test. So, this is a very simple straight up unit test. Is there a question? Okay. Now, for the mesh, the first action that you need to do after you, I am not talking about a unit test for the discretization itself, but you can have that done too, but let us go on to the next functionality that we want to have, and that is we want to make sure that, because these are halo, these are stencil operations, you need halo cells or the guard cells around your domain section where you want to compute where the halo come from the neighboring sections. So, here what you can do is you initialize, you pick a known function and have two variables. In the first variable you initialize only the interior, in the second variable you initialize not just the interior, but also the halo, and only on the first variable you execute the guard cell fill and you compare the values, and right there you have a unit test for halo cell fill or guard cell exchange. So, that is my second unit test, right. Now, I can run a test for hydrodynamics by running this problem in uniformly discretized mode, because in a uniformly discretized mesh, that is all the functionality you need. So, if you so we write a code for the expression of distance traveled by the shock independently, then we use our shock hydrodynamics solver to run the Sedov problem. At some time t, we compare the solution against the analytical solution. Now, here what is happening is that if both ghost cell fill and equation of state tests pass, then if there is a failure, we know for sure that that failure is occurring because of the hydrodynamics. So, this is the idea behind scaffolding, in that the hydro test is built upon the scaffolding provided by the equation of state and guard cell fill unit tests. Next, we want to we also want to be able to test the functionalities of AMR now. So, here is where we continue to build scaffolding further, in that the same halo cell functionality that works for the uniform grid will also work for AMR, because it is the same principle, right. Each one of the blocks in AMR you can fully initialize with the functions, one variable with internal, one variable including the guard cells, and continue that way. So, now the additional two functionalities that we wish to test for are the resolution of the quantities at fine coarse boundaries and regridding. So, now what we do is we run the following tests. We run the unit tests for equation of state and grid, and then we run the hydrodynamics with uniform grid. Then we run the hydrodynamics with adaptive mesh refinement, but regridding turned off. And then we run hydrodynamics, full hydrodynamics with full AMR and even the regridding turned on. Now we can reason about, we can apply reasoning to figure out where the error is, because if the first 3 tests pass and the 4th test fails, then we know that error lies in the reconciliation of fine coarse quantities, and if the first 4 tests pass and the 5th test fails, we know that the error lies in regridding. So, here what we have done is we have continued to build our scaffolding to the point where even though our individual tests are getting more and more complex, they are still able to pinpoint the cause of error without having to actually run through the steps of debugging. I mean, you will eventually have to run debugging within the code component to find out exactly where the error occurred, but you have already pinpointed a section of the code where this error could be occurring. So, that is a big win. Okay. Now, for the legacy code, now the test development is a challenge in its own right, because here now we are getting into black box testing in the sense that we do not wish to modify the code in any way, and still we want to be able to test for the code. So, here what the situation is going to be is not only that you do not have a test, you probably do not even know how internals of that system are working, and you do not really want to touch them very much, right, because who knows what you are going to break if you touched it. So, this is one methodology that might work, and I have successfully applied that in E3SM, the climate modeling code, for isolating one particular module from the rest of the model, because when I came into looking at this code, the situation was that even for your simplest debugging, you had to run the whole model with all of the dependencies, which would take a number of minutes to build, and then because you were running the whole model, it would not fit on anybody's laptop. You had to run it, put it on a queue in the cluster and wait for it to run, and only then you would. So, every step in your debugging process had a turnaround time of hours. And so, that was clearly an untenable situation, and we needed to find a way of developing a test that would isolate that section of the code where this particular scientist was working and speed up their debugging time. So, this is the methodology we came up with, is that if you think about this tree as the whole structure of the code and say I want to just test this part of the code, what you do is you separate that, think about as a separate section of the tree, and there just before your code comes into and invokes that section of the code, you take a state dump, a complete state dump of the state of the program at that point, and turn it into a readable file, right. Then you write a reader for this state dump, such that that data can be read in and can be used to populate the data structures for this section of the code. So, that is our driver. The next thing that happens is, so where this invocation was happening now, instead of that there is a driver. What may also end up happening is that this code though may have had a dependency somewhere in this part of the code. And so, you need to be able to gather information about this part of the code as well, which can be done in one of 2 ways. One is that you can either take a dump of the output coming from this section separately and make that a part of the state that you have dumped here, create a stub for this. So you can create links into the dependencies, or you can create a stub, and then all of these things put together give you a test. So, now what you are doing is, instead of running the model from initial conditions, you are effectively restarting your code from an intermediate state of its running, and when you are doing this, you are only invoking the code section that you are interested in, and then you will dump an output from that code section. So, another aspect of this process is also that you should have dumped not just the state here, but the state here also before you started to mess around with the code, because that would become your baseline for comparing against any new run of this particular component as you do as you are debugging it. So, this can become a test for a legacy code where you are doing black box testing. An important component in all of these tests is something that we have at times forgotten to do to our cost, is to verify that the test actually fails when the code is defective. So, we wrote a test, the test was passing, we were happy, we did not realize that the test was passing even when the code was not right. So, that is an important thing to remember. Okay. So, how do you build your test suite? That is an equally important thing, and this is a craft. This is not too much of a science, it is a craft, because what you want, most of the codes that you use in extreme scale science tend to be the kind that have many different functions, many different physics solvers. And it is not just that individual physics solvers need to work correctly, it is that they need to interoperate correctly, and they can be combined in many different permutations, and they need to work right in all of these various permutations in which you can configure them. So, we realized that for codes that are really big, we need two levels of testing. Both of them need to be automated, but one is much more scheduled testing and the other is continuous integration. Now, you have all heard about continuous integration, and continuous integration is great, because what that means is anytime there is a change to your code repository, whether you are doing it through depending on your policy, let us assume that the policy is always that a pull request is merged. As soon as the pull request is merged, the test suite starts to run and reports the results in a matter of few minutes, and that's your continuous integration, that it's invoked, it's triggered every time change happens in the source. The catch with that is that in order for it to be effective in a team that is in a large team that is working, the continuous integration test needs to be small. It needs to return within a matter of a few seconds, if not a few minutes. When you are working with large complex codes, their test coverage is complex enough that sometimes running through the entire test suite might take hours, and therefore, that is not conducive to continuous integration. And so, there you have to have continuous integration mixed with these automated scheduled testing, which are much more comprehensive tests and provide more comprehensive coverage for your test. In the codes that I have worked with, that includes E3SM, a code at Berkeley Lab, and then Flash, and then Flash X. It is these automated scheduled testing is where we really rely upon for code quality control and correctness, and we run them not just on one platform, we run them on multiple software stacks, because again different compilers have different level of tolerance for errors, and the more you exercise the code, the more likely you are to find defects in your code before they become a huge issue. So, these two pictures that I have are just snapshots of what, say, a Jenkins snapshot of a test suite run might look like. So, this is a Flash X test run that has taken 5 hours and 11 minutes to complete, and here is a picture from a CI run that Jared's runtime does. So, they're visually different, and they serve different purposes as well. Okay. So, in your test suite, there are certain rules of thumb that work very well. One of them is that a mix of different granularities works well, because you always want the the total running time of your test suite to be as small as possible. You need to have unit tests that isolate components and subcomponents. You need to have integration tests that exercise the interoperability and permutations and combinations. In scientific computing, you need to have restart tests as well, and this is because this is something that most people won't tell you, and this is because typically you are submitting your jobs in a batch run, and so your simulation or whatever analysis you are doing is likely not going to be completed in a single instance of being on the queue, which means that you need to be able to restart from an intermediate state, and so you need to make sure that your code also restarts transparently. So you need to test for that restart happening transparently on your code all the time. And as I said before, they need to be simple, and they should be able to, they should have quick pinpointing ability. So how do we determine what tests are needed for the code? There are code coverage tools that tell you about the lines of code that have been exercised in the code. That is again your first line of defense, and these utilities G-curve and L-curve are, they come with the I think new, yeah, they do, and they give you information about the lines of code that have been covered. So that is, like I said, the first line of defense, but it isn't comprehensive because it doesn't, they don't test for interoperability and functionality. So that is, for scientific codes, that's an equally important thing, is how do you make sure that you are testing for all possible ways in which your code may be exercised. So we developed this one methodology that I will briefly tell you about. You can develop your own, but this is just an example. It is not any standard method, but this works for us. It might work for many of you. So what we do is we create a matrix, and we have certain of the code functionalities that we want to check interoperability of along the columns, and certain others along the rows. And then what we do is we pick tests and we mark off spots in this matrix where that interoperability is exercised, right. So for example, here these are the names of the tests. So the test that is CL, it is exercising interoperability between hydro and AMR, equation of state and AMR, burn and AMR, and particles and AMR. Similarly, SV test is exercising the same functionalities with uniform grid. There is the WD test that is exercising some of the other, and this is not exhaustive by any means, but this is an example. So, and then we have a methodology for picking order in which we pick tests to mark off these spots in the matrix. So, of course, first are unit full module tests that are, even though they are not really strictly speaking unit tests, but they are exercising say just one physical module separately, and so those are the first tests we pick. Then as a next step, for the remaining spots that are still empty, we pick tests that are very sensitive to perturbation, because if you want to minimize the running time of your test suite, you want a test that fails quickly rather than runs for a while before failing. So you pick things that are very sensitive to perturbation. In the next step, we pick the tests that are most stringent for certain types of solvers, which means they exercise them in the ways that are that will exercise the corner cases, and then we pick the least complex tests that will exercise the remaining portion, that will cover the remaining parts of the matrix. So this is the methodology by which we build test suite. I should hurry up. So some other good rules of thumbs is that you should test your tests, which means that they fail when they are supposed to. You should have regression tests to ensure that bugs are not creeping in. You should be testing regularly, because if you are not testing regularly and a lot of development is going on, then there is no purpose to having tests. The whole purpose of testing is to catch an introduced defect as early as possible, and that can only happen when you are running regularly. Automate testing, because who has the time to spend on running a bunch of tests? And we do that. I do that even when I am doing the development. I have my automated set of tests that I want to run, because changes that I am making may be touching more than one way of generating the code, so I just run with them. And then you always utilize physics and math based strategies to build your tests. So, to summarize, a testing strategy is essential for producing trustworthy software. You need to invest the needed time to thoroughly test your software. Different challenges are associated with different types of code, and you have to evolve and customize your testing strategies accordingly. So, it is not very useful to get distracted by the technology that you should be using PyTest versus C-test, etc. The important thing is that you are testing, and then you pick and choose the tool that best meets your needs. And here are some of the resources. With that, I am done. I will take questions if there are any. Yes?
Is there a good way to get code coverage on GPU code?
Sorry?
Is there a good way to get code coverage on GPU code?
The code coverage is the same, right, for whether it is for the GPU or the CPU, in that you think about the ways in which the code can run on the GPU and use something either like the matrix or yeah.
I think he's referring specifically to tools like gcov.
Yeah, like there's no
GCOV,
So-
GCC has a flag to generate code coverage and NVCC does not.
Yeah, it's so we were looking at this and we don't know of anything for GPUs that currently does code coverage. There's several issues there.
One of the ways in which I do these things is also, if you're using offloading, then the code should run on CPU also, and you can check for coverage that way.